Okay. Hello everyone. Let's talk about performance. The main question when like after we've made the single cycle processor is how do we actually measure its performance? Well, one way to measure the performance is to think of basically how many instructions can it actually do per second. And the way we can quantify that is actually by measuring the time delay that it takes for any specific instruction to be executed. And this delay is actually dependent on, in particular, something that's going to be the same for all of these guys. It's going to be the clock speed. So Um, basically, how when we think of how an instruction is ends up working, basically the clock triggers a change in the program counter. The program counter is fed into the instruction memory. The instruction comes out. Different parts of the instruction go to different parts of the circuit. For example, this one, which is the RN register goes through the register file, goes into the ALU, optionally goes to the ALU result, and then into read data, and then it goes all the way into, say, register file. So it has a definite start and end for, say, a specific path that a specific instruction a specific path that it takes. And if you may recall correctly, there is in your logic classes, there is a specific path like this called the critical path, which is for a combinational circuit, the path of the longest delay. And if you turn into sequential circuits, then um, this critical path is the one that decides how fast your clock can be, because there's things like hold time, and there's things like combinational delay, there's clock to Q delay. So all of those have to be taken into account for the single cycle processor for us to decide how fast the clock speed can be. And since, for example, the data memory will have delay on the order of like hundreds of nanoseconds, and these guys will take maybe like, I don't know, 50 picoseconds or something like that, longer for the register file. But the thing is, the clock for the single cycle processor is going to be based on a very long critical path, which is going to make its clock very slow. So say the let's call T delay the worst case logic delay until some relevant output change plus some hold time and other similar constraints. We can say that the frequency of the clock that is allowable is actually 1 over the that allowable clock period, which is the delay time plus plus other hold time, but we're not talking about hold time right now. But okay, so that's the allowable clock frequency. And we can say that for any single program of interest, the thing that we actually want to know for like there is no perfect benchmarking program for the performance of a processor. It's just that you want it to run a program that you want it to run in the fastest time possible. And so it depends on the program that you are running, um, like how good the performance of a computer is. But in general, The execution time for any specific program is based on the number of instructions of that program times the um, well, I would say average clock cycles per instruction, but the number of clock cycles taken by the processor per instruction that it's executing times the number of seconds that it takes for a clock cycle to finish. And this is actually just the reciprocal of the frequency, because this is in seconds. And okay, I just sorted it to CC here, and the number of instructions. But I would note here that for these guys, this is actually average, because some processors are designed in such a way that the instructions do not take the same number of clock cycles per instruction. So the average clock cycles per instruction over the instructions that are given to you by the program, this thing depends on that. So maybe that doesn't make too much sense right now. So let's talk about the microarchitecture types. So these are the three most common architecture types. There's others, but those are, I guess, I would say most of them are proprietary or not too popular. But this one I would say is really really popular. Um, but you can see here a blue shape. It's not a square. A blue quadrilateral is symbolizes a single clock cycle, and the number inside it symbolizes the instruction that it is currently executing. And we are executing three different instructions on these microarchitectures. So for a single cycle processor microarchitecture, this is what it does. It takes one clock cycle per instruction, but as mentioned before, this clock cycle it takes very long, because you you traverse everything in the data path before you get to you traverse everything in the data path to get the worst case delay, which then decides your clock period, thus making a single clock cycle very very long. But in return for that, each instruction only takes one cycle. So we can take note, okay, this is where it ends. Say this is the time dimension. This is where it ends. For the multi-cycle microarchitecture, it takes multiple clock cycles to execute any specific instruction. You can see here it takes 3 here, takes 4 here, and it takes 4 here. So the multi-cycle architecture takes more than one clock cycle per instruction, but it also still has a uniform clock. There's still the clock ticks at the same rate always. Just the thing that's different is each instruction can now have a different amount of time that it's taking on the processor, because you can take different amounts of different numbers of clock cycles for a specific type of instruction. Maybe some instructions are easier to execute, some instructions are harder to execute. So you take more cycles for those instructions than say for these easier instructions. So that's basically the motivation for the multi-cycle operation. And you can see here, since we were able to shorten this, the easier instruction 1 compared to the harder instructions 2 and 3, we were able to save a little bit of time compared to the single cycle processor. This is, of course, with the overhead that designing a multi-cycle processor is a little bit more complicated than, say, designing a single cycle processor. Now, the pipeline processor, as you can see over here, it's just like the multi-cycle processor, but what it basically does is it executes multiple instructions in different parts of the data path at the same time. So here, this guy is using, say, the first part of the data path. Then here, Instruction 1 is using now a different part of the data path, while instruction 2 uses the part that it was using before, and so on and so forth. And now you can see that even though it takes 4 clock cycles to execute a single instruction, and the clock speed is not any different from the multi-cycle operation, you can see here that we actually managed to finish 3 instructions in a much faster time than we actually should ever have executed it. It's basically like trying to, it's basically similar to a single cycle processor where this clock period is now your new clock period. But even though pipeline processing sounds great on paper, and it is great practically, but it has a lot of design problems that you need to solve. And Sir Ryan in the um, I think in the fifth week or next week we'll be discussing this pipeline processor. I will be discussing multi-cycle next. Um, but yeah, there's a few problems that come with the benefits of pipeline processors. But basically, this is how you have trade-offs in the computer performance. For example, multi-cycle processors have more clock cycles per instruction, but the frequency of the clock is also higher. Or if you want me to say, the reciprocal is lower, at least compared to this guy. So these are the trade-offs that come with the types of computer microarchitectures. There is also an impact on the performance depending on the choice of the instruction set architecture. So you may have heard this before, but I'm going to repeat it again. There are these types of ISAs called the complex instruction set computers and the reduced instruction set computers. So complex instruction set computers have a wide variety of available instructions, and because of that, you can it's like say Python, where you have a lot of different APIs, so you can just call one function to do many things, very specific things, but still many things, so that the code is very compact because you have access to a lot of APIs. That's basically what complex instruction set architectures have. Now, reduced instruction set computers, on the other hand, have less instructions, but because it has less instructions, it's easier to design, and you can bring up the clock speed even higher because of this lower complexity, lower circuit complexity. So, real world examples, CISC, an example of a CISC computer is the x86. If you're using an Intel processor right now, that is basically what it has. You can also maybe see that your program files, parenthesis x86, those are parenthesis x86 because those executables are basically written in x86 machine code. Risk, on the other hand, is what we are studying right now in 153, which is ARM. Maybe V7, maybe V8. Um, this guy is used by Apple with, I think, virtually all of its stuff. That's Apple A, Apple H, Apple M. Apple M is the latest one. Um, there's also Qualcomm's Snapdragon. You may see it in some other mobile devices now as well. This uses the ARM ISA as well. MIPS is a lesser known but it's a beloved instruction set architecture that was very popular in the past and is still being taught today as one of the simplest and the first RISC architectures. And there's also RISC-V, which is basically something that the 196 and 196, 199 students um, tend to work on. And the reason that they work on this is because, well, it has an open license. So basically, if you try to make money with it, you don't have to pay anything. Um, we can access the instruction set manuals and stuff for, say, ARM and x86, but the thing is, you can't make money with you can't, like, you're not allowed to make money with those. There are licensing problems with them, and the main thing about risk 5 is that, its license is open, you can use it. So, okay, comparing CISC and risk, at least, okay, let's pretend we were in the 1980s. um okay, yeah, for now, let's pretend we are in the 1980s, where risk was first introduced by, say, some guy. I don't exactly remember the name anymore, but he's quite good because apparently the guy who developed Risk is also the guy who developed RAID, redundant array of inexpensive disks. So if you're curious about that, just Google RAID. It's actually one of the most genius things I've ever seen. Um, but anyway, CISC. Okay, the number of instructions for CISC is lower because, try to imagine it like a Python API. You can just use a single function to do a lot of things. Risk, number of instructions, there's a lot because, it has reduced number of instructions, so you have to write everything explicitly. The number of clock cycles per instruction. Nowadays, this isn't particularly too different between CISC and RISC because it now depends on, the processor. But basically, in the past, the number of clock cycles per instruction was higher for CISC than it was for RISC because of all the complicated decoding stuff. Nowadays, say for x86, for example, the pipelining, the way these things are pipelined is, well, still very, very complicated. But it's a very complicated design process that they've already done. So it's all good for them, and basically they've managed to put it so that the um the disadvantages of CISC is now very much minimized at this point. And on the other hand, naman, Risk has encountered a lot of extensions lately. So, say for example, for ARM, you have ARM Neon, which handles um, floating point operations. You have RISC-V, vector extension, which handles vector operations. And those guys, basically, they're making your RISC computer CISC because they're adding more special instructions to your reduced instruction set. So the instruction set is no longer particularly reduced. So actually, the line between CISC and RISC is starting to blur. But still, this is back in the 1980s, so none of this has happened yet. But this is the motivation for the rise of Risk to begin with. Now, it used to also be that you can bump up the clock frequency much, much higher for Risk than you can for CISC, and that's because of the circuit complexity. Of course, now the main there are other problems with trying to bump up the clock even more, which also eliminated this um, kind of advantage of Risk, or maybe not eliminated, but it basically minimized the difference between CISC and Risk uh, in this manner as well. But because PCs nowadays, they go from 2.4 gigahertz to 5 gigahertz, and like around that frequency. Wait, no, this is Wi-Fi, no? But if I remember correctly, my PC runs at 2.2 gigahertz. But anyway, ARM Cortex processors, x86 processors, they all run in around the same frequency range nowadays. Okay, design complexity. CISC is much, much, much more complicated. There is an MIT lecture that discusses x86 instruction set. And if you'd like, you can try to search that up on YouTube. But I would say CISC is very, very complicated. Risk, sakto lang. That's what we've been talking about. It kind of looks complicated, but when we made the single cycle data path, I was like, okay, that's kind of simple, I guess. So yeah, okay, and so that's it for computer performance. Next, we're going to discuss multi-cycle architectures.